Hello. We are going to continue about statistics in this video, and what we have done up to this point is basically MLEs, a little bit of MLEs, and a little bit of estimation and stuffs like that. So let me recall what we have done until now. It was MLE, it was point estimation, so these are the things we have done, and we would like to do some more. Now, what happens is once we try to get hang of this test statistics and this stuffs like this, what we actually want is to understand the ideas behind these topics, right? So in statistics, what happens is when you have a data set and you're trying to manipulate with it, you're trying to get some information about how the data set acts, how it works, or you maybe graph it. So let us say you have a data set x1, x2. Let me write it down. We have a data set x1 up to xn. Now in this data set, what we can do is we can see that x1, x2 up to xn is a data set, and the properties described by this data set could be as follows. The mean is written like this with the x bar. It is called the sample mean because we believe that this data set x1 up to xn, if it is not the population, then it was taken from the population by some sampling method. Now there are a lot of sampling methods in existence: uniform sampling, random sampling, and then there is collective sampling and lots of others of them. Okay, cluster sampling. So a lot of types of sampling are there, and they were taken by any one of those methods or a completely new one maybe. But anyway, they are members of the population and they represent a sample of the population, right? Our target is to understand the features of the population given this sample. So firstly, the sample mean is this. Okay, this is the sample mean, and we also know the variance is let me first I have already defined you moments, but I'll just write it down again. The average, which is given like this average e of x, or the expectation of the data set, if the data set is continuous, maybe discrete here in this case, then it is basically equals to the sample mean, right? And this sample mean is the best estimator for the population mean. So if the population mean is mu, this means that expected value of x bar is simply equals to mu. Okay, now there are a few other things we should note, that we have studied this kind of things, and what we would like to understand is what is a z score now. So we would like to understand z score. So how is a z score related and what is a z score? So z score comes from the z distribution. It is a standard normal distribution. So let me give you an example. Given x is a random variable following normal distribution with parameters mu and sigma square. Okay, find the z score for, okay, so we want to find the z score for some value, and we are not entirely sure how to do that. But if you are asked to find the z score for some x equals to k, then the z score for x equals to k would be k minus mu by sigma. This is the z score. So what it means is that the z score basically follows the normal distribution. Now, how to find probabilities of certain things? So suppose we have to find probability of x less than equals to alpha. Okay, so if this is the case, then what we do is we see that we subtract by the mean on both sides first, then we divide by the standard deviation, now since x is if x is basically directly normal variable, it's fine. But if x is just a representative of a sample which has n entries in total, then what we do is this: we multiply it by root n on both sides, and same here. Now this x minus mu by sigma multiplied by root n, now let t equals to root n by sigma into x minus mu. We can show that t is standard normal, that is t goes from normal of 0 comma 1. So when this happens, what we see that therefore probability of x less than equals to alpha, this value would just be probability of t less than equals to root n times alpha minus mu by sigma, right? And for the standard normal variable, what the answer would just be minus infinity to root n of alpha minus mu by sigma 1 by root over 2 pi e to the power minus x square dx, or it can also be written as phi of root n into alpha minus mu by sigma, where this phi represents the standard normal CDF, where phi is this, right? Now the integration parts and all these things, the prerequisite for integrals would be embedded from my previous videos as well. You will get that. But the question here remains that when phi and when we have the standard normal variable, we can easily find out, and this is essentially what we call the z score. The values of the standard normal variable for different probabilities have already been listed out quite often, and what we can do is we can understand if this function really is required in order to understand all the different properties of any probability we ever get. And thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives, There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel. So when you have the mean and the variance of each of them, they come from the same distribution, which are IID. Of course, I want to write IID here, and this sample mean is mu. So basically what I want to do is E of xi is mu. Okay, so when this happens, we can write the CLT states that this, or in other words, or what you can do is you can write like this: probability of x bar less than some t can be written as probability of z, where z is a standard normal variable, less than t minus mu by sigma square by actually sigma by root n, not sigma square. So let me correct this part. Sigma by root n. Right, and this only happens when you have limit n tends to infinity. So it basically becomes phi z of t minus mu by sigma by root n. So this is how the CLT works. So it can be for any distribution. It may be for a binomial distribution, it may be for a Poisson distribution. It wouldn't matter really, but it can be for any distribution. And the prerequisite for this variance and exponential stuff would be given at the end of the video as well, so you can check that out as well. So this is the CLT, and we will talk more about it and solve maybe after that, or maybe some problems at the end. But this is it for this one. So enjoy the prerequisite. Any constant c, this equation becomes true. So since we do not exactly know what the constant was, so we just put a plus c. So this answer would be just x square by 2 plus c. Imagine that x square by 2 plus 5 or x square by 2 plus 2, both of them would give you on differentiation the value of x, right? Similarly, if you were to do 1 by x dx, the answer would just be ln of x plus c, right? Okay, so we do know about this basic differentiations, and let me now iterate some of the facts. Integration of f of x plus g of x dx. So when there are two functions added, we can obviously write them as integration of, it's actually plus minus, even for minus it works, integration of fx dx plus minus integration of g of x dx. Okay, if there is any constant c such that you have c into f of x dx, where c is independent of x, is just a constant. When I say constant, I mean it is independent of the integral variable. It will just give you c into integral of fx dx, right? So these are the two things we shall remember. There is not a hard fast rule for integrating product of two functions or division of two functions, but what we do have is something we will learn in the later chapters, which we call integration by parts, which is not really a rule which will readily integrate anything for you, but yes, it does help you integrate a lot of functions. So how do we actually integrate? So there are some ways to do that. and we will learn those methods slowly one by one. So let us integrate some of the basic integrals first. Let me write down the integrals. So let us try to evaluate all three of them. The solution for 1, as you can see, it's just e to the power 2x dx. What we can do here is we can write e to the power 2x dx equals to e to the power 2x divided by 2 plus c, right? Similarly, for number 2, what we can do is we can write integration of sine of x plus cos of x dx, and we can write integration of sine x dx plus integration of cos x dx. As I already mentioned, that we can separate the two functions which are in addition or subtraction form and integrate them separately. Okay, so as we have learned, the integration of sine x would be just minus cos x dx. There is no dx because it is out of integration, plus integration of cos x is just sine x. And you might wonder that there should be two constants corresponding to both of them, but we do not really care, because since they are constants, we can just write a plus c at the end of the whole integration, because it doesn't really matter because c is unknown, right? So whatever c1 here and c2 here plus would give, probably capital C would also give you the same result. If you even if you write two constants, it can be absorbed into one, right? So this is the answer for second one. And for the third one, it's try e to the power log x plus x dx. But we observe that e to the power log e of x, which is the natural logarithm, is just x. So x plus x dx, which is basically 2x dx, and we can see that the constant 2 comes out and it's just x dx, and x dx has a form which is x squared by 2, and there would be a plus c outside. This would mean you will have the integral as x squared plus c. This is your answer. So these are just the basic applications of the direct formulas. So this is not at all integration, it's rather like we are trying to revise some of these formulas and some of these formulas from this table, right? But now let us come to the actual part of integration. So when integrating, obviously you are trying to find a function which when differentiated will give you back the integral, right? So if you're trying to integrate some fx dx and what you get in answer is a function g of x, what you actually mean is when you differentiate g of x, you should get back the function f of x, right? Or in other words, there exists a function gx such that g prime x should be equals to f of x dx. This also means that when you have an integral of a differentiation, that is, if you have integral of f dash x dx, where f dash x is already the derivative of fx, it would just give you fx back. This is what integration means, because it's just the opposite of differentiation. Okay, so this is very important to understand, that obviously when you are trying to integrate a function, you are trying to find another function which when differentiated will give you back the integrand. Now let us go to some of the topics. Method 1, and by far the most important method, which we are going to learn extensively in this video and in future videos. Rule of substitution. Rule of substitution, right? So how do we find this? How do you find the rule of substitution? So consider an example. Let us say we are trying to evaluate the integral I equals to 2x e to the power x squared dx. Now this is not a part of any of the elementary functions that you have seen, but it's rather a composition of two, and e to the power x square, remember that e to the power x's integral is e to the power x, but in case of differentiation of e to the power x square, you could have just used the chain rule, right? But it's not so simple here in integration, because there is no definite rule for integrating e to the power x square dx. Neither there is for integrating x into e to the power x square dx, right? So we need to make our way out of it. So what we do is we try to see what is the anomaly here. So if it were e to the power x only, it would have worked, and if this x were somehow magically gone, so this x squared term needs to be substituted. How do we do that? So we just substitute it. So let us introduce a new variable, which is y, and which equals to y equals to x square, right? Now only y equals to x square would not give you an answer, because you cannot just substitute it as y. That is why what we do here is we use d of y, we differentiate both sides to find dy by dx. So in differentiate y upon y in terms of x to find 2x, but then take this dx to the other side to find dy equals to 2x dx, right? And then you can see that this integral is basically equals to dy into e to the power y, which is just e to the power y plus c, or e to the power x square plus c. So this is the way we will try to do all the problems, and from the next section forwards we will be doing a lot of problems in rules of substitution. This is just an introductory video, and in this video, as I have said, we will try and do problems on methods of substitution, and we will try to do as many problems as we can so that we understand method of substitution in a more clear way. But notice that this lecture obviously requires you to have a little bit expertise on differentiation, because as method of substitution is completely dependent on derivatives, because every time you are going to substitute a variable for some other variable, what you're going to do is to find the derivatives of both the sides and use the differentiation. And you also need to realize what derivatives or what substitutions are we going to make, so that the integral may be reduced to a simpler one or a more elementary one. That is the entire goal. So let me give the heading. So method of substitution. Okay. So in this method, let us try and understand what to do by choosing some of the problems. Let us say we have a problem x plus 4 whole cube dx. Now this problem can be solved in multiple ways. The first way will obviously being you would try to evaluate this x plus 4 whole cube as a trinomial. Like what you can do is use the formula for a plus b whole cube and use it as x cubed plus 4 cubed plus 3 into 4 into x whole into 4 plus x, and what you would get is x cube plus 4 cube plus 12x into 4 plus x, right? So you can break it down as x cube plus 64 plus 48x plus 12x square, and then you can integrate all of the terms separately, because all of them are just constant times some power of x, and we very well know that the integration of any power of x can be found out, because integration of x to the power n is simply x to the power n plus 1 by n plus 1 plus c, right? So obviously this is one method to do, but integration makes it a lot simpler for us, because when we use the method of substitution, what we try to do is we do like this: we substitute y equals to x plus 4. Okay, now when we do the derivative on both sides, what we get is we get dy equals to, now the derivative of this x plus 4 with respect to x would be equal to 1 plus 0, right? Because the derivative of x is 1 and the derivative of 4 is 0 dx. So what we do get is dy is equal to dx, right? So what we are trying to do is, when we are trying to convert the whole integration from a variable of x to a variable of choice y, we also need to find the dy in terms of dx. So the dy would be in some function of dx. Here it is equal, which is another case, which would simplify our integral like this: x plus 4 whole cube dx would just be equal to y cube dy. because you see we have substituted. Now it might seem a little bit dumb because, well, you do see that we could have just simply found out x to the x cube dx, right? But it's not the case, as you will see. Now the integration of y cube dy is just y to the power 4 by 4 plus c, and this can be done because the variable of integration is dy here, right? And now after you've got the answer, you put back all the substitutions. So y was substituted as x plus 4, so what you do is x plus 4 whole cube by 4 plus c, which is the answer, right? So okay, so this makes x plus 4 whole cube by 4 plus c, and these are the two ways that we can evaluate this integral, right? Okay, so let us move on to another example which would be a little bit more trickier, or maybe a bit tad harder than this one. Let us evaluate sine of ax plus b for real numbers a and b. Okay, for real numbers a and b. Okay, so how do we do that? Well, obviously in that case also what we are trying to do is we are trying to substitute this thing ax plus b, because were it only sin x dx, it would have been easier, right? So let us name the integral as I, and let us substitute y equals to ax plus b. Now, as in the previous problem, what we are going to do is we are trying to differentiate both sides to find an expression for dy in terms of dx, right? So differentiating both sides, we get dy is equals to a into dx, because the constant b would disappear and a into x's into differentiation is just a, and we have an extra dx always, as I told you. So dy would be a dx, or in other words dx should be equal to dy by a. Okay, now this would turn our integration something like this. It would be sine of y, because ax plus b is y, and dx would be dy by a, and this would give you 1 by a sine y dy. Now we know the integration for sine y, it is just minus cos y, so the answer would be minus cos y by a plus c. And it's time to put back the variable which we substituted, which would give us cosine of ax plus b by a plus c, which is the answer for our integration. So as you see, like this kind of equations are this kind of integrals can be solved by using simple substitutions, but obviously there are harder ones. So let us try to find out another integral. Evaluate integral of 1 by 1 minus 2x dx. Now what does this resemble of? Firstly, because the simplest way we can evaluate an integral or to find out what to substitute is to find out the most recent or the closest integral which it resembles to. So as far as I can tell, this resembles to something like this, right? Whose integral we known as ln of x. So if we can somehow transform it in this form, that 1 by some variable and d of that variable, we can do that. An obvious way to do this is to substitute 1 minus 2x, and since it is linear, we substitute y equals to 1 minus 2x. Now y equals to 1 minus 2x would give us a pretty easy way to evaluate this integral, because when you differentiate both sides, what you get is dy equals to minus 2 dx, right? And this would give you dx equals to minus dy by 2. Using this I should be equal to 1 by 1 minus 2x is just 1 by y, and dx is just minus dy by 2, right? And so the constant minus 1 by 2 comes out, and we have 1 by y dy. Now this would give us minus 1 by 2 ln of y plus c, and it's time to put back what we have substituted, which gives us minus 1 by 2 ln of 1 minus 2x plus c. So you understand that we are in every problem, what we are trying to do is we are trying to reduce the integral by using some magical substitution, or rather a rational one once you try to get the hang of it, to reduce it to an elementary integral we know of, and then evaluate it directly, and then put back the value of the variable once it is out of the integration to get back our result. So this is what we call the method of substitution. We'll see a lot more examples in the coming sections, obviously. So the general version for this one would be, the general version for this type of integral is dx by ax plus b, and you can evaluate it. So let us name it as I. Substitute y equals to ax plus b. Now when we substitute y equals to ax plus b, we can have dy equals to a into dx, right? Then I should be equal to integral of dx is dy by a, so put a 1 by a outside, dy here, and this should be y. So this would give you 1 by a ln of y plus c, and if you put back the value, it would give you 1 by a ln of ax plus b plus c, which is the answer. Okay. Now next example what we can get is something like this. We can try and find out some of the basic theorems regarding this, like so this one is a tad harder, but what I'm going to teach you in this, in regard to this problem, would be something that you should remember in your way along. So this type of an integral is not something where you just magically find the substitution, but rather you literally look for something. So that something is determined by the following theorem. Theorem says that if you have f of gx into g prime x dx, this is the form of the integral, which as you can see is the chain rule, then this is equal, then this is basically equal to the integral of f of gx d of gx, or you can say this is equal to f of y dy, where y equals to gx. So you just need to integrate the function f. If the function f is integrable to you in an elementary form, it would be done, right? Okay. So what we are trying to find is, if we can find something, some function which is a function of something, and the derivative of that function is already given along with dx, we can directly substitute that function. Why? We can see why. So given integral is I equals to 2x into root over of 1 plus x square dx, and we can substitute y equals to 1 plus x square. Why are we doing that? Because see, I realize that the integral of 2x into root over 1 plus x square can be solved if we were to eliminate this root over 1 plus x square thing. So when I substituted y equals to 1 plus x square, I saw that the derivative of 1 plus x square is just 2x, which is given along with dx. So 2x dx would be substituted into a single dy, which is what we wanted, which is basically the form of this function, right? So the derivative of 1 plus x square is already given outside. So when we do dy, what we get is 2x dx, and that is helpful because this turns into root over y into dy, where 1 plus x square got to y and 2x dx was written as dy. And this is an easy one because this is just y to the power half dy, and using the rule you can find it as y to the power half plus 1 divided by half plus 1 plus c, which is basically y to the power 3 by 2 into 2 by 3 plus c, which is the answer, right? So this is the integral and this is the answer, and we can just substitute back to get our answer in terms of x, obviously. So it is basically 2 into 1 plus x square to the power 3 by 2 whole by 3 plus c. This is our integral, right? So this type of integrals can be solved, but you need to be a bit cautious about them. So let us do another one. Evaluate dx. So we want to evaluate 4x by root over of 2x square plus 1 dx. Again, it should be noted that ddx of 2x square plus 1 is equals to ddx of 2x square plus ddx of 1, right? And ddx of 2x square is just 2 into 2x, and ddx of 1 is 0, which gives you 4x. So you see that 4x is already present. The derivative of the term of 2x square plus 1 is already present. And if that is so, what we can do is we can substitute y equals to 2x square plus 1, and thus we see that dy is equals to 4x dx, and this would turn our integral into something like this. But this just only means that it's y to the power minus half dy, and using the rule we can write it as minus half plus 1 by minus half plus 1 plus c, which is basically y to the power half, and this becomes 2 because it's a half in the denominator, and we can substitute back our answer to find it's just 2 into root over 2x square plus 1 plus c. If you differentiate this using the chain rule, you would find that the answer is basically 4x in divided by root over 2x square plus 1, which is amazing because differentiating something is very easy while integrating something is insanely hard, just because of the methods or the ways you have to look for, right? Okay, let's do another one. Evaluate sine of root x by root x dx. Now again in this one, as you can see, the only portion that is not going with the integral is the root x inside the sine, right? And we are kind of sure that whatever else is present in the integral should be the derivative of that, right? So let's see. We observe ddx of root x is just equal to ddx of x to the power 1 by 2. Now we have learned previously that the ddx of x to the power something is just the coefficient comes out, so the coefficient comes out, and the coefficient the power comes out as a coefficient, and the power is reduced by 1, which means it is half into x to the power minus half, or in other words 1 by 2 root x, right? So if we were to differentiate, what we would get is something like this. Let y equals to root x, then dy should be equals to dx by 2 root x, right? But we see dx by root x is also present, so what we get from this equation is dx by root x should be equals to 2 dy, and we can absolutely put this to get the integral as I equals to sine of y, because root x is y, into 2 dy. Since 2 is a constant and is in multiplication with the rest of the integral, it comes out, and we only have to integrate sine y dy, which is just minus cos y, so it's minus 2 cos y plus c, and putting the value of y back, what we get is minus 2 cosine of root x plus c. This is the answer, right? So you see, like, this kind of integrals can be solved, but then again we have to be a bit cautious. So let us solve a lot more problems. Example 7. I will try to do this as much as I can so that you get the idea of method of substitution completely. And if you have any trouble in evaluating derivatives, please go back to the last videos to find out how to evaluate a certain derivative or how to do complex derivatives as well. Okay, so example 7, evaluate integral of 2x e to the power x square minus 5 dx. So let us denote the integral by I, so that I is equals to 2x into e to the power x square minus 5 dx. Note that now again in this integral we are trying to see that since the derivative of x square minus 5 is just 2x, what we can do is y equals to x square minus 5, which should give us dy is equals to 2x dx, right? Then on substituting, I is equal to e to the power y and the 2x dx becomes dy, right? And you know the integration of e to the power y is just e to the power y plus c, and you put in the value which was x square minus 5 plus c. So this type of integrals, if you find the derivative of a term directly present inside the integral, try to substitute for that term so that you can reduce it into a common integral or an integral that you know of, okay? Because only then would it be easier for you to find out what to do. So we will continue our examples, but first let us learn one more thing. Let us do one more example, then from the next video we shall also do all the other indefinite integrals that we are required to do in the method of substitution, but also we will do some of the definite integrals, and we will learn how to do the definite integrals as well. So let us do this. This would be example 8, right? Yeah. So we'll continue from example 9 in the next video. So this would be the last example for this video. So let us do this problem where we have integral of cosine of x dx by 1 plus sine x. So this one looks a bit more tedious than before, but note that ddx of sine x is just cos x, right? So as we can see, cos x dx is present in the numerator and 1 plus sine x is in the denominator. So if derivative of sine x is cos x, then derivative of 1 plus sine x should also be cos x, right? So rather than going for the substitution y equals to sine x, what we can do is we can directly go for the substitution 1 plus sine x, then let y equals to 1 plus sine x, and from that we get dy is equals to cosine of x dx. This would give us our integral as y equals to integral of dy divided by y, which is just the integral. This integral is evaluated as a natural logarithm. Hello everyone. So let us begin, and we will be studying a little bit about statistics, and we'll be starting our chapters from where we left off in probability. In the meanwhile, we have done a bit of integration and a bit of calculus to add our supplementary skills, and also what we did was we made sure that the probability portion got into multiple random variables and stuff like that. Now our entire goal of this was to study higher probability and statistics, which we shall begin, and for that we need to know the basic to intermediate portions of statistics and how all those probabilistic criteria and solutions would actually work in a real life scenario, right? So I'll just write it down and let us see. So what we are doing is we are beginning a bit of statistics here. So in statistics we deal about something called data. When I say data, what I mean is we have clusters of points which represents some identity or some information about a certain quantity, and we would like to investigate about those data points or those cluster of points, and we would like to find certain information about it. For example, what we can do is we can measure heights of certain people. So let's say we have 10 people, and what we do is we measure heights for each of them. What we can do is we can name the heights measured as x1, x2, and all the way up to x10. Let this be the data points. Okay, so what are these? These are the data for our sample experiment or whatever we're going to do. Now using this data, what we can do is entirely a different subject, because there are a lot of things we can try on this data, but for the basics, for the sake of basic statistics, what we can do is we can find the mean, the mode, the median, we can find the skewness, the kurtosis. Also we can see if they fit into any probability distribution, and moreover what we can do is we can find probabilities of certain heights being improbable or certain heights being like very likely, right? And maybe there are more than 10 people, maybe there are like 1000 people, and we did a random sampling of those 1000 people, and we selected 10 people at random, and then we selected the heights, and from this heights what we need to do is we need to give a general idea about what would happen to the heights of the other people, or you can say the height of the population, which is of the 1000 people. Can we get an idea about the height of the population from the from the data points secured in this sample? That is the ultimate question. That is, let us say we were trying to investigate some statistics about the whole country, and there are a lot of people in the country, right? So let's say there are 100 crore people right now, for example, and what we want to do, we cannot sample 100 crore people, that would take a lot of time, and that is why we are being realistic here. We are not really being mathematical, because in mathematics we can even sample 10 to the power 100 people, right, with in a finite number of years, but that doesn't make sense. So let us say we can sample 1 lakh people or 100,000 people, and we would like to get an idea about the whole population from the sample of this 100 lakh people, 100,000 people. And what we would like to do is we would like to select them randomly and uniformly from the population, so that no selection is biased, every selection is uniform, and every selection is equally likely. When we do that, the question is, can we get the idea about the whole population? Ideas like what is the average height of the population, ideas like what is the height that goes on the furthest, above which range do we have a 20% chance of getting a certain height, and stuff like that. So we shall begin with something called mean. So what is the mean? Let me write it down. Right. Similarly, the median. So if this is the mean, the median is given by and after we are done sorting the data in ascending order, what we need to see is the middle points. Now since there are an even number of them, there are two middle points, that is x5 and x6, and they contribute to the median m, which is given by the average of this two. Okay, and if it were not the if it not were even, let us say we had 5 quantities, then there is only one middle number, that is the third one, so we only take that one, right? So it makes sense, because what we understand from this kind of criteria is that we need to be clinical about our data set, and there are a lot of things we can do with the data, and it's usually a good idea to sort them into ascending order before doing any calculations, because it helps us figure out how the data is increasing. We can also graph the data. So this mean, this median, whatever we're talking about, these are called statistics. So statistics are basically a function of the data points. So an example of a statistics would be, so covariance of x comma y would be e of xy minus e of x into e of y, right? Where e of y is defined as integral over all r y into f of y dy, and e of xy on the other hand is basically a double integral where fxy x comma y is the joint distribution of x and y. So this provides the way to make sure that we have our expectations correct, and obviously integration is very much required in each of probability and statistics courses, because integration and derivative, they form the base of calculus, and in each step we shall find ourselves to be doing some kind of integration or differentiation, right? So that is one way. Now let us see what we can do with some of the things we have here. Let us begin with a topic here. So what is point estimation again? So we have talked about it before in probability, but let us talk about it in detail here. What is point estimation? Suppose we have B, a point estimator, for a parameter theta. Now what we do know is bias of an estimator is as follows. So bias of an estimator is given by expected value of the estimator minus the estimator. You see, so that is how bias is defined, and we call it unbiased if bias is 0. So we call so if this happens, we call our estimator unbiased, right? Now we can take an example to see that why this is the case and how we can prove such questions. So let us take a small example. So that is the question in we need to show, not of itself, obviously it's unbiased estimator of theta equals to exi. The parameter is theta, which is equals to e of xi for every I, right? So how do we show that? We see that e of this phi cap is basically e so now we use the properties of expectation as follows. Therefore we see that e of phi cap is basically equals to theta, which means it's a phi cap is an unbiased estimator of theta, and that is why it is basically unbiased, and our problem is solved. Now this is how we solve this problems, and showing that something is an unbiased estimator specifically involves finding the expectation of the point estimator, and this expectation may well involved some kind of integration or summation, which we have discussed before, I think, and those are required. Now after this, what we will learn is the mean squared error. So this is the mean squared error, because phi cap minus theta is the error that we make when we are going to estimate theta based on phi cap. Because see, phi cap is an estimator of theta, right? But since we say estimator, we are not really guaranteed that phi cap would always equal to theta. So it estimates theta, so there can be some error, and that error is given by phi cap minus theta. And mean squared error is basically we square the error first, which is phi cap minus theta squared, and then we take the mean of it. And in statistics and probability, when we say mean, we always mean the expected value, because the parameters and everything else, they can be a continuous random variable or a discrete random variable kind of thing, and we need to do integration or summation over that, right? So that is one way. Also, what we can find out from this is, so the MSE is basically the equal to variance of the estimator plus bias of the estimator squared. This is another way to find out that. Now, here comes an important property of showing something is a consistent estimator. So our topic is how to show how to show if some estimator is consistent, right? To do that, what we can do is we say minus theta is greater than equal to epsilon, and this is equals to 0, of course, for all epsilon greater than 0. So this is basically the definition for the epsilon delta case and stuff like that. And we can make sure that this works. So let us do one example for that. Suppose x1 x2 all the way up to xn be a random sample with mean e of xi equals to theta and variance of xi equals to sigma square. Okay, we need to show that is an consistent estimator of theta. And obviously we first do the integral definitions of this. We want to say that this is, since let fxx be the common PDF, then exi is simply fx dx, while variance of xi is x minus exi squared fxx dx. Okay, and we want to show that theta n is a consistent estimator, where theta n is basically equals to the sample mean. So given and we would like to show that this is the consistent estimator of exi, and let exi be equals to theta, which is also given. So therefore we need to show the following. So then probability that theta n cap minus theta absolute value is greater than equal to epsilon is equal to, so what we do see here is that they have a common PDF and they would like to, they can be treated as equals, right? Now this means that what we can do is we can use the Chebyshev's inequality here, because we see that E of theta n cap is E of 1 by n summation of I equals to 1 to n xi, which is 1 by n and this becomes theta, right? Therefore using Chebyshev's inequality we have less than equals to variance of theta n by epsilon square. And now variance of theta n is basically variance of x bar by epsilon square. Now what is variance of x bar? Variance of x bar is simply equal to and this would be 1 by n square variance of summation from I equals to 1 to n xi, and this would be n into sigma square, so it becomes sigma square by n, right? Therefore probability that theta n cap minus theta is greater than equal to epsilon is less than equals to sigma square by n epsilon squared. Therefore limit n tends to infinity, probability that theta n cap minus theta is greater than equal to epsilon is less than equals to 0. And this means that obviously since probability can always be is always greater than equal to 0 as well, therefore limit zero. So theta n is an estimator of theta. and this is proved. And added with this would be also the required videos for integration as well, because we needed it. Integrals of the form where you have two functions fx into gx dx. What we do here is we try to name or label the functions as function 1 or function 2, and once we do that, we can have a easier rule to find out the integral in terms of another integral, which might be easier to solve. So as of derivatives, it does not obviously give you a direct answer, but it rather gives you a newer integral which might be easier to solve, and we have a rule for it. The rule is something like this. The rule is called ILET. I for inverse functions, L for logarithmic functions, A for algebraic functions. Algebraic functions means function of polynomials like x cube, x to the power 4 plus 2 and something like that. Logarithmic is involving log, inverse is involving sine inverse x, cos inverse x, tan inverse x, like that. So the inverse trigonometric functions. T is for only trigonometric, and E is for exponential. So why is this order important? This order is to choose the function that you choose is which is higher up the list, which is like if the function, there are two functions in multiplication form, which is one of them are inverse and another one is algebraic, then you would have the inverse function as the first function and the algebraic as the second function. So if the function is higher up on the list, you would name it as function 1 and the other one would be function 2. So let us name here fx as function 1 and gx as function 2. Then what it gives you is function 1 directly comes out into integral of function 2 dx minus integral of derivative of function 1 into integral of function 2 dx multiplied by derivative of function 1 and the integration of this whole. So this is how it works. So you take the first function and you multiply it by the integral of the second, and you subtract from it integral of derivative of the first function into integral of the second function. So let us take some examples so as to understand how this works. Example 1. Let us find out the derivative of x log x dx. Okay, so identify x is an algebraic function, right? Ln x is logarithmic. So which one is more up the list? Obviously L, right? So L should be treated as the first function and x should be treated as second function. So denote the integral by I. Integral by I, and what we do get here is I equals to integral of x log x dx. Given that log x, we are denoting log x as first function, x as second function, which means we should have first function into integral of second function minus integral of derivative of first function, which is just 1 by x, into integral of second function and the integral of the whole thing, right? So integral of x dx is just x square by 2, right? So it should be x square ln x by 2 minus, we have already found the derivative for log of x, which is 1 by x, and again integral of x is x square by 2. So in this inner integral you do not need to include the constant plus c, so we are basically trying to just find the integral and accept the constant. So 1 by x into x square by 2 dx, and as we can see, this becomes x square ln x by 2 minus integral of this x is cut off, it's x by 2 dx, which can also be evaluated because x square log of x by 2 minus this is x square by 2, so this is x square by 4. Now we can include a plus c to complete our answer. So x log x could not be evaluated otherwise. The only way is to guess the function whose derivative is x log x, which is kind of impossible. So we do not really need to follow that strategy, obviously, but this would give us the answer, right? Okay, so let us try to find out some more problems. For the next problem, what we do need is this: ddx of tan inverse x is equals to 1 by 1 plus x square. We are going to prove it, but first understand that since the derivative of tan inverse x is 1 by 1 plus x square, this also means that integration of 1 by 1 plus x square is equals to tan inverse x plus c. Okay, and how do we prove it? Okay, so let y equals to tan inverse of x. Then what we see is x should be equal to tan of y, right? And what we are trying to find is dy by dx. So let us see how to find that. And the derivative of tan y is sec square y, if you remember it from the derivative section. So differentiating both sides, we get dx equals to sec square y dy, and sec square y is just 1 plus tan square y dy, and so dy by dx would be equals to 1 by 1 plus tan square y, but tan y is just x, so it is just 1 by 1 plus x square, right? So the derivative for tan inverse x, which is dy by dx, is 1 by 1 plus x square. Proving it, and all the other inverse functions can be proven in the same way, and corresponding to that we can find this integral. Evaluate integral of x to the power 4 by 1 plus x to the power 10 dx. Now at first glance, obviously that we want to eliminate the or substitute for the denominator, but we see that the derivative of 1 plus 1 x to the power 10 is not x to the power 4 dx, right? Or not any constant multiple of x to the power 4 dx rather. But what we can do here is denote the integral by I, then what we get is this: capital I is equals to integral of x to the power 4 dx divided by, and we can write x to the power 10 as x to the power 5 whole squared, because in that case what happens is, if we substitute y equals to x to the power 5, what we get is dy is equals to 5 into x to the power 4 dx, right? And what we want is the value of x to the power 4 dx. So therefore x to the power 4 dx should be equal to d of y by 5. So our integral becomes I equals to integral of, this thing becomes dy by 5, and the denominator just becomes 1 plus y square. So taking the constant outside, we get 1 by 5 dy plus 1 by y square. Now since we already know the derivative integral for 1 by 1 plus y square is tan inverse y, but if we hadn't known that, what we could have done is we can use trigonometrical substitutions in problems where we have something of the form 1 plus x square or 1 plus y square in the denominator or in the numerator. Because if you substitute, and remember, obviously you can make as many substitutions as you can, there is no rule of making only a single substitution for a single integral. As you can see, I am going to make a second substitution now. I am going to substitute for the substituted variable itself. So substitute y equals to tan theta, where theta is another variable. Then dy would be equals to sec square theta d theta, if you remember the derivative of tan theta, and sec square theta is just 1 plus tan square theta d theta, and as you know 1 plus tan square theta is just 1 plus y square d theta. So therefore taking this on the left hand side, we get dy by 1 plus y square equals to d theta. So this whole thing becomes d theta, right? So therefore I equals to integral of d theta by 5, and integral of d theta by 5 is just theta by 5 plus c. But theta as you know, if y is tan theta, then theta would be tan inverse y. Then the answer would be tan inverse y by 5 plus c. But we also need to put back the value of y, which we substituted as x to the power 5. So the answer would be tan inverse x to the power 5 whole divided by 5 plus c, which is our answer. Right? Okay. So this is another problem, and let us do another one. This one would be from the section of IBP. So obviously, whenever you're facing or you're in a situation where you are in exam or some problem solving session, you might not be given the topic, right? So you might have to figure out on your own how to do a certain problem of integration. If it's a definite integral, or even if it's an indefinite integral, you might have to substitute for something. You might have to do integration by parts. So there are various ways to do an integral, and you need to figure out which way works for you, which way actually solves the integral, because other ways might actually make you go round and round and come back to the same integrand again, right? So let us evaluate x sin x dx, and after that we'll do a more complicated version of this. So denote by I the integral, and whenever we see functions which are product of two different kinds of functions, we try to remember our eyelet rule, where we obviously know which one to take first function and which one to take second function. So in the eyelet rule, as you can see, eyelet, the algebraic function comes first after the trigonometric function. So algebraic function should be part 1, function 1, and the trigonometric one should be function 2, right? Then we have I equals to x into integral of sin x dx minus derivative of x, which is ddx of x, into integral of sin x dx, and whole thing is dx here, right? Now integral of sin x is minus cos x, so this is minus x cos x dx, minus x cos x, minus ddx of x is just 1, and integral of sin x is again minus cos x, right? Then as you can see, it simplifies considerably into minus x cos x, and this minus make it a plus, and 1 into cos x is cos x dx, and you do know the integral for cos x dx, which is just sin x, right? So the answer is x minus x cos x plus sin x plus c. So this integral is something which just comes back around its own, because the trigonometric functions, the sin x and cos x functions, generally they come back around its own when you integrate them enough number of times. So for example, they have a period of 4 on integration. So if you integrate sin x 4 times, you will actually get the same result. So let us try to find out something else here. Next problem would be integral of e to the power x sin x dx. Now this is a problem where you would know why the denote by integral I is of paramount importance. Okay. Let's see. Denote the integral by I. Then what we have is I is equal to e to the power x sin x dx. Now if you remember in the rule eyelet, e, that is for exponential functions, that came last. So obviously e to the power x is going to be the second function here, and sin x is going to be the first function. So applying IBP, or applying integration by parts, what we have is this. I is equals to sin x into integral of e to the power x dx minus d dx of sin x into integral of e to the power x dx dx, right? So what we do get is integral of e to the power x is just e to the power x, so it becomes e to the power x sin x minus differentiation of sin x is cos x, so cos x into e to the power x dx. Now this is another integral. So again we apply the same integration by parts technique with cos x as the first function and e to the power x as the second function. Notice how we have to do integration by parts twice here, and we are doing it, as you will see why. It becomes cos of x into integration of e to the power x dx minus the integration of d dx of cos x, and as you know integration of e to the power x dx is just e to the power x. I'll just write e to the power x dx here. So it becomes e to the power x sin x minus e to the power x cos x, and d dx of cos x is minus sin x, and minus becomes plus. It becomes e to the power x sin x dx. And if you take it away from the bracket, what becomes is e to the power x sin x minus e to the power x cos x minus integral of e to the power x sin x dx. But notice that this is the integral that we started with, right? So this is denoted by I, which is a variable. So this becomes e to the power x sin x minus e to the power x cos x minus I, and on the left hand side we have I. So solving for I, what we get, we get 2i equals to e to the power x sin x minus e to the power x cos x. Therefore I is equal to e to the power x whole into sin x minus cos x by 2, which obviously there is a plus c, which is the answer. So this is one of those integrals where you have to do integration by parts twice to get the answer. So this is a problem where we have basically the integral coming back on its own, and then we have to solve it like that. So this happens a lot of times. So let us do another problem. This one would be a bit tad harder than the last one because of the concepts involved. Evaluate integral of sine of log x plus cos of log x dx, right? Now obviously what we want to do here is, first, as this is not any function that we can be reminded of, this is not any elementary function, neither does it have substitution that is very clearly visible. So obviously the derivative of log x is also not present, right? So naturally the first thing we would like to try is to substitute for log x and see if that makes any difference, right? So obviously I is equals to integration of sine of log x plus cosine of log x dx, and substitute y equals to log x, which will give us dy equals to 1 by x dx, right? Therefore this integral would become, and from this you can see that dx is basically equal to dy into x, but we need it in terms of y, so x is basically e to the power y, so dx is basically e to the power y dy, right? So the integral becomes sine of y plus cos of y whole into e to the power y dy. And this is time to introduce a new theorem, or rather a lemma, which is helpful sometimes. So lemma: for a differentiable function, function f of x if I is equal to integral of e to the power x into f of x plus f dash x dx, then the integral is I equals to e to the power x into fx plus c. So if you have an integral in this form, the answer is simply e to the power x into f of x. So the proof is necessary, so we shall do the proof here. We start with the integral, given integral, and we shall see why this lemma is important in solving this problem, this particular problem. So given integral is I equals to e to the power x whole into f of x plus f dash x dx. Now let us separate it into two different parts, that is e to the power x into f of x dx plus e to the power x into f prime of x, or derivative of fx dx. So let us try to break down this second integral. Name this integral as b. So b equals to integral of e to the power x into f prime x dx. If you apply integration by parts here with e to the power x as the first function and f dash x as the second function, what you do get is e to the power x into f dash x dx minus derivative of e to the power x is just e to the power x and integral of e to the f dash x and then a dx outside, right? Now we know that the integral of a derivative is just the function itself, so it just becomes e to the power x into f of x minus this becomes integral of e to the power x into f of x dx, right? So if we put the value of b there, we see that I is equals to integral of e to the power x f of x dx plus b, where b is our desired integral which we have just evaluated using integration by parts, and which becomes e to the power x into f of x dx plus e to the power x into f of x minus integral of e to the power x into f of x dx. And as you can see, these two integrals cut off because they are exactly the same thing. So the answer is just e to the power x into f of x, which is the answer for the integral. Now in our given problem, in our given problem, we have I equals to integral of e to the power y, it was, into sine y plus cos y, right? So let f of y equals to sine of y, then f dashed y would be equals to cosine of y, and therefore I equals to e to the power y into f of y, which is sine of y, and cos y is the derivative, so f dashed y, right? And from the lemma we see that this is basically equals to e to the power y into f of y plus c. Putting back y, we get e to the power, and what was y again? Y was log of x, right? So we get e to the power ln x into f of ln x plus c. Now e to the power ln x is just x and f of ln x is just sine of ln x plus c, which is the answer to our integral.